Hello. So today in this class, we are going to discuss about the Markov graph, how to draw Markov graph of a periodic point of period 5 for simple explanation and periodic point of period 9 also. And then we are going to find out the fundamental cycle, definition of fundamental cycle. So then we are going to discuss the Markov graph of a periodic point of period 9, but not having periodic point of odd period less than 9 and greater than 1. So yes, let us go to the video that I created. Yes. Yeah, first Markov graph. Markov graph consists of vertices and edges. Let us see an example of a periodic point of period 5. There are 5 distinct points of the orbit of a periodic point of period 5. The distinct orbit points are labeled in their natural orders as x1, x2, x3, x4, and x5. Then the basic intervals or vertices, capital I's, are formed by joining the consecutive points of the orbit. So there are 4 basic intervals I1, I2, I3, I4 for a periodic orbit of period 5. In general, there are n-1 basic intervals or vertices for a periodic point of period 9. Next, how to draw a directed edge from the vertex ij into a vertex ii. We draw a directed edge from ij into ii if f of ij covers ii, that is f of ij is a superset of ii. For example, if f of I1 covers both I2 and I3, then there are directed edges from I1 into I2 and I3. So a cycle in a Markov graph is a closed path starting from a vertex, moving along edges and ending to the same vertex. It has 2 representations. One is chain representation, J0, J1, J2, J0. And the another one is graphical representation, which is shown below. In this example, the chain representation has 3 edges and 4 vertices. The vertex J0 appears twice, one in the beginning and the other at the end. It shows the path is a closed path. It is a cycle of length 3. The graphical representation has 3 vertices and 3 edges. So it is a cycle of length 3. If the chain representation starts from the vertex J1, then J1 will appear twice, one in the beginning and the other at the end. So why do we change the nomenclature from vertices from I's to J's? Well, J's are same as I's. And in this notation, the vertices J's appears in the same in their order. Also, graphical representation has some understandable figure over I's. Interval covering relation, let us see, and drawing of directed edges. We know that there is a directed edge from J1 to J2 if f of J1 covers J2. Let us see how it happens. C maps to f of C and f of C maps to f to C. So by intermediate value theorem, f takes values between f to C and fc, the interval covered by the white brush, that is f of J1 covers both J1 union J2. So there is a loop in J1 and an edge from J1 to J2. So next is fundamental cycle. So how to find a fundamental cycle? Now let us see how we find fundamental cycle of periodic orbit of period 5. There are 4 vertices. The phase rotate is given by f of x1 maps to x2, f of x2 maps to x3, f maps x3 to x5, and f maps x5 to x4, and then f map x4 to x1. So if we take c is equal to x1, which is an endpoint of I1 or J0, then f of c is an endpoint of I2 or J1, f2c is an endpoint of I4 or J2, so F3C is an endpoint of I4 or J3. F4C is an endpoint of I3 or J4. Lastly, F5C, that is equal to C, is an endpoint of I1 or J0. So C is an endpoint of J0 such that FKC is an endpoint of JK. So K going from 0 to 4. Therefore, the cycle is a fundamental cycle for the given periodic orbit of period 5. So that is how we find out a fundamental cycle. Okay. So yeah, next let us see. Yeah, Tarkovsky, theorems. Now the second video, let us see. Periodic orbit of period 9 and its Markov graph. So there are 9 points in the orbit. It is arranged in their order as shown in the video. Okay, so the intervals I1, I2, I3, up to I8 we have. Okay, so now we are going to show that the periodic orbit doesn't have any period or less than 9 and greater than 1. I mean, now C is the center point, then F of C, F3C, F5C, all odd on the right, all even iterate on the left. So C goes to F of C, then F of C goes to F2C, F2C goes to F3, 4, then 5, then 6. So if the orbit has in this pattern, okay, the orbit has in this pattern, then there is no periodic point of period 7, no 5, no 3, okay, then all other periodic points are there. So now let us see how to draw the Markov graph according to the orbit structure we have. So there is a loop in J1, then there is an edge from J1 to J2, from J2 to J3, J3 to J4, J4 to J5, J6, J7, J8 to J8, then J8 to J1. Then again, there is an edge from J8 to J7, J8 to 3, J8 to J5. See, why do we have the edges? It is explained here because f of J2 is a superset of J3. Therefore, there is an edge from J2 to J3. So next, now let us see the fixed point. Why do there is a fixed point? So let us refer to the Markov graph again. So again, so there is a loop in J1. So there is a loop in J1 that is a primitive cycle of length 1. So therefore, there will be a fixed point. So a primitive cycle of length 1 guarantees the existence of a fixed point. Okay, so there is a loop. Why? Because f of J1 covers J1, therefore there is a loop. So we have a loop and the existence of fixed point is guaranteed. Okay, a shell loop at J1 implies f of J1 is a superset of J1, which guarantees a fixed point. Okay, now let us go to the next video that the existence of periodic point of period 2. So period 2 cycle is there, or primitive cycle of length 2 is there. Let us see where is the primitive cycle of length 2 in the this one. There is a loop from J8 to J7. So then J7 to J8, So there is an edge from J8 to J7 and J7 to J8. So it is a primitive cycle of length 2 because we have 2 edges here. So therefore, we will have a periodic point of period 2. F of J8 is a superset of J7. Therefore, there is an edge from J8 to J7. Again, f of J7 is a superset of J8, or in another language, we call it f of J7 covers J8. So there is an edge from J7 to J8. So in totality, we have a primitive cycle of length 2. Therefore, there exists a periodic point of period 2. So that is the thing. Okay, so next is, let us see, there is a periodic point of period 4 also. So again, we are going to refer to the Markov graph. We are going to refer to the Markov graph, and we are searching from the Markov graph a primitive cycle of length 4. So if there exists a primitive cycle of length 4, so this is yellow highlighted part, Ji to J5, J5 to J6, J6 to J7, then J7 to J8. This is a cycle of length 4. It is a complete cycle because starting from J8 and ending at J8 again. And it is of length 4. So it is a primitive cycle of length 4. Therefore, there exists a periodic point of period 4. So existence of a primitive cycle of length 4 in Markov graph guarantees the existence of periodic point of period 4. That is the thing, that is the theorem we have learned. So yeah, let us see. This is a cycle. Let us see how we draw this cycle here again. So from Ji to J5, J5 to J6, J6 to 7, 7 to I. So therefore, it is a primitive cycle of length 4. So next, let us see periodic point of period 6. That means we are going to find out from the Markov graph, we are going to find out a primitive cycle of length 6. Yeah, let us go back to the Markov graph again. We have to search for a closed part of length 6. So this yellow highlighted part, you can count the arrows 1, 2, 3, 4, 5, 6 from 7 to 8, not from 8 to J7. Okay, so from 7 to 8, one arrow, yellow highlighted arrow is there. So we have a primitive cycle of length 6 in this case. So therefore, there will be a periodic point of period 6. So existence of a primitive cycle of length 6 guarantees the existence of a periodic point of period 6. That is the thing. So that is the point about the this Markov graph. So Markov graph easily predicts the existence of periodic point. What we have to do is that we are going to search the primitive cycle of desired length. Next, let us go to same Markov graph again. Let us search for primitive, cycle of length 8. Then there will be a periodic point of period 8. Okay, so so this is the Markov graph again. Now let us see the yellow highlighted part. Yeah, from Ji to J1, J1 to J2, J2 to J3, J3 to J4, J4 to J5, J5 to J6, J7, and Ji. This completes the part or cycle. So it is a primitive cycle because you cannot make this cycle by repetition of smaller cycle, So therefore, it is a primitive cycle of length I. So it guarantees the existence of periodic point of period I. So that is the thing, that is the thing. So primitive period of period I cycle exists. So therefore, there exists a periodic point of period I that directly comes from the Markov graph, this primitive cycle. Now, let us see the primitive cycle of length 9 that will guarantee you the existence of periodic point of period 9. And indeed, this is a orbit we are talking about periodic point of period 9 orbit. Okay, so where is the primitive cycle of length 9 from the Markov graph? So what is the difference between the earlier primitive cycle of length 9 and this primitive cycle of length 9? So now this cycle start from J1 and there is one loop in J1. So J1 to J1, then J1 to J2, then J2 to J3, then J3 to J4, J5, J6, J7, J8, and go back to J1. So it completes a primitive cycle of length 9. Therefore, there exists a periodic point of period 9. So that is what we have learned about the fundamental cycle and Markov graph and a periodic point. So the Markov graph explains very nicely about the Sharkovsky theorem. Now, so now the question is, can you draw from this Markov graph? This is the Markov graph. This is the Markov graph of periodic point of period 9. From this Markov graph, will you be able to find out primitive cycle of length 3, primitive cycle of length 5, primitive cycle of length 7? So you cannot find any primitive cycle of length 3, 5, 7. Okay, there exists a primitive cycle of length 1. Therefore, this loop J1 to J1, it is a primitive cycle of length 1. So the existence of fixed point is there, that we have already talked. My question is, it is impossible to find a primitive cycle of length 3, length 5, length 7. These are all odd number less than 9 but greater than 1. So since there are no primitive cycle of length 3, 5, and 7, we cannot have periodic point of period 3. Okay, so this is a typical Markov graph of a periodic point of period 9 in which there is no any periodic point of period odd period less than 9 and greater than 1. Okay, so if a periodic point of period 9 doesn't emit any other periodic point of period 7, 5, 3, then the corresponding Markov graph will be in this form. Okay, so that is the beauty of Sharkovsky theorem, and proving Sharkovsky theorem using this Markov graph easily, very self-explanatory note. The Sharkovsky theorem can be proved using this Markov graph. That is the whole idea of this discussion. So as I told you, it is not possible to form a primitive cycle of length 3, 5, and 7 from this Markov graph. And then, how about other? So we can have a primitive cycle of length 1. We can have primitive cycle of length 2. So there is a periodic point of period 2. We can have primitive cycle of length 4. So there exists a periodic point of period 4. We can have primitive cycle of length 6. So there exists a periodic point of period 6. We can have primitive cycle of length 8. So there exists a periodic point of period 9. Okay. So, but we cannot have a primitive cycle of length 3, primitive cycle of length 5, primitive cycle of length 8 also. So in the Sharkovsky ordering of natural number, there is 9, and all other natural number beyond 9. For those natural number, we can have a primitive cycle of the desired length of the desired periodic point. Okay, so in the ordering, in Sharkovsky ordering, 3 is greater than 9, 5 is greater than 9, 7 is also greater than 9. All other natural number are less than 9. So we can have periodic point of period, any other period which is less than 9. In Sarkovsky ordering, I'm talking about in Sarkovsky ordering. In Sarkovsky ordering, we know that 3 is greater than 9, 7 is greater than 9, and 5 is also greater than 9. In Sarkovsky ordering, 9 is greater than 2, 1, 4, 6, all these natural number except 3, 5, and 7. So therefore, if there exists a periodic point of period 9, then all other periodic points are there, whose period is less than 9. That is what Sarkovsky theorem says that. And we have demonstrated here that it is not possible to draw, primitive cycle of length 3, primitive cycle of length 5, primitive cycle of length 7, especially for this periodic point of period 9 orbit. So yeah, how we form any other periodic point, we can see this one. See, this is a primitive cycle of length 9. Okay, therefore existence of periodic point of period 9 is guaranteed. Okay, then how to find? Yeah, one more loop adding to the J1. One more loop adding to the J1, we have a primitive cycle of length 10. Therefore, there exists a periodic point of period 10, and 10 is less than 9 in Sarkovsky ordering of natural number. And then, how about 11? Yes, 11 also. So, in order to find a primitive cycle of length 11, we add up one more loop at J1. So, we get a primitive cycle of length 11, and therefore, there exists a periodic point of period 11 also. And 11 is less than 9 in Sarkovsky ordering of natural number. Okay, how about period 12? We can add one more loop at J1, and then we get a primitive cycle of length 12, and then we have periodic point of period 12. Okay, so that way we can add up one more loop at J1, and we'll get a primitive cycle of length 13, and there will be a periodic point of period 13 also, and it goes on infinitely many times. 100 also, you can add up one more loop at J1, and you will get a primitive cycle of length 100, and then you will get a periodic point of period 9. So you can do this infinitely many times, and all this number in the Sarkovsky ordering of natural number are less than 9. The only problem is there 9, 3, 5, 7. We cannot have periodic orbit of period 3, periodic orbit of period 5, periodic orbit of period 7. Okay, because 3, 5, 7 are natural number in Sarkovsky ordering, which are greater than 9. So so that is what yeah, so as many loops in J1 as we want to get n period. That is easily we can do it at J1. So the whole idea now, the whole idea, can be understood easily. Yeah, if we go back to the orbit, yeah, how to draw, you see how to draw a periodic orbit of period 9. So there are lots of periodic orbit of period 9. Okay, specifically for this type of orbit, for this type of orbit, there are 9 points in the orbit: x1, x2, x3, x4, x5, x6, x7, xi. So if the arrangement of the orbit is in such a way that, so this x5 is C, and it goes to 6, and 6 goes to 7, like this. Okay, yeah, you see this one. So now the x has been replaced by their orbit, iteration. So C is in the middle, then C goes to f of C, that is on the right. Okay, then, so if the pattern in this form, if the orbit is in the form, in the following form, C goes to f of C, and then f of C goes to f to C, and then f to C goes to f3C, and then f3C goes to f4C. Okay, then f4C goes to f5C, like this. It continues this beautiful configuration as phase portrait. Then finally f8C, that means f9 of C goes to C, because it is a periodic point of period C, it should come back to the original C. So if the phase portrait of the orbit is in this particular form, there are lots of phase portrait of periodic point of period 9, okay? But if the phase portrait of the orbit is in this particular form, okay, then there will not be, periodic point of period 3, there will not be periodic point of period 7, there will be not be periodic point of period 5 also. But all other periodic point of period n, which are less than 9, can be found out from the Markov graph. That is the theorem. That is the thing about, you see. So see, let us see, this is the end point. See, this interval is called J1, okay? So J1 has two endpoint, one at C, another one at F of C. So, and the image of C is here, F of C, and then image of F of C is F to C here, okay? So one endpoint, C image is here, FC's image is here. So by intermediate value theorem, uh, the function f takes values in between this endpoint, okay, in between this endpoint. That means the image of f of j1 covers the interval j1 and j2. So that means j1 covers, f of j1 covers j1, there is a loop, and if there is a loop, there will be a fixed point, okay? And then uh, f of j1 covers j2, so there exists a is from j1 to j2. So that is the thing, yeah, that is the fundamental thing, how to draw the Markov graph, okay? So you can refer this video again and again, and uh, you can try to understand all these things, the fundamental cycle, and then how to draw the Markov graph, and then from the Markov graph, how to find out cycle of desired length, okay? Cycle of length 8, cycle of length 10. So those things, yeah, we have explained. So you can try and watch it again and again until and unless you understand, and you can call me back, we can have discussion about these things. So I should stop here, okay? All the best.